There are many sensors where the fundamental change in the sensor is a change in resistance. A photoresistor, for example, changes resistance depending on how much light is hitting it. A thermistor will change resistance depending on its temperature, and a strain gauge will change its resistance depending on what strain it's put under. We can't read the resistance of a sensor directly, so we first have to convert it to a voltage that we can read in an analog to digital converter, for example. To do that, we typically employ a fairly simple circuit known as a wheatstone bridge. A wheatstone bridge works as follows. We have an excitation voltage, which I'll call VEX, and we run it through several resistors arranged as such, where we have a ground down here. If each one of these resistors is some nominal resistance R, then we know that the voltage at this node here, which we'll call V1, and the voltage at this node here, which we'll call V2, will be the same. On the other hand, if we make one of these resistors a variable resistor, for example, if we make this a photodiode or a photoresistor or a thermistor or a strain gauge, then this resistor can vary, and when it varies, the voltage in V2 will vary, and we'll be able to read some change in voltage, delta V, across these two nodes here. So let's figure out how we can calculate exactly what that change in voltage will be. Let's say that our variable resistor changes by some resistance, we'll call it delta R, and that delta R will be small in comparison to the nominal resistance R. We know that delta V will be equal to V2 minus V1, and we can find those using the standard formulas that we use for a voltage divider. So for example, voltage of V2 will be the excitation voltage times R plus delta R over 2R plus delta R. And the voltage of V1 is just going to be 1/2 Vx. After a fair amount of algebra, we can show that this is equal to delta R over 2R times 2R plus delta R, all of that times our excitation voltage. But we said that delta R was small compared to R, and so we can ignore the delta R in the denominator here, and we'll say that we end up with the change in voltage is equal to the excitation voltage times delta R over 4R. Now, if you're using strain gauges, the problem is complicated a little bit by the fact that strain gauges not only respond to strain, but they're also affected by temperature, and the temperature effects can be pretty significant and have to be taken into account. Luckily, if you can arrange your strain gauges such that you can have two that have opposing effects, then you can simplify the problem substantially. For example, I'll draw up here a cantilevered beam, and we want to measure the strain in this beam as we apply a force down on the end. Let's say we put a strain gauge on the top, which will elongate as we push down with the force, and a strain gauge on the bottom that'll get shorter as we push down on the end. And as you know, if this beam is symmetric, that the strain on the top will be exactly opposite the strain on the bottom. The nice part about this is that any temperature effects will affect both of the strain gauges in the same manner, and so that won't affect our voltage at V2. So what we do then is we attach the top strain gauge down here where the original strain gauge was, and we add our second strain gauge in the other half of that leg of the wheatstone bridge. So to analyze this one, we know that delta V equals V2 minus V1, which is equal to the the voltage at V2 is the excitation voltage times R plus delta R over the resistance of the entire length of that circuit, which is 2R, minus the voltage in V1, which is just going to be R over 2R, which equates directly to VEX times delta R over 2R. We can, if we really want to, we can add another set of strain gauges. If we had a second strain gauge on the top here, and these are actually next to each other, even though I'm drawing above and below. Above and below. We can, we can attach the other strain gauge on top here to this leg of the wheatstone bridge, and the other one on the bottom to this leg of the wheatstone bridge. And when we do that, we end up with the change in voltage is equal to delta R over R. And I will leave it as an exercise for you to show that this is indeed the case. Whoops. Sorry. All of this times delta R over R times the excitation voltage, of course. So let's go back to the case where we had just the two strain gauges and work through a short example. In this case, we know that delta V is equal to the excitation voltage times the change in resistance over twice the nominal resistance. We can write this as excitation voltage over 2 times delta R over R. Now, for most strain gauges, delta R over R is related to the strain by what's known as a gain factor. That is, delta R over R is equal